All right, let's talk about this massive, invisible engine that's running our planet 24/7. It's the system that dictates our weather, carves out our landscapes, and it's even shaped human history for thousands of years. It's called global atmospheric circulation, and we're about to pop the hood and see exactly how it works.
So, have you ever pulled up a map and just wondered about this? I mean, how can you have the unbelievably lush Amazon rainforest sitting so close to the bone-dry Atacama Desert? It seems totally backward, right? Well, it's not a paradox. It's actually a direct result of that global engine we're exploring. And by the time we're done here, you'll get it completely.
Okay, so first things first, where does the power for this planet-sized system even come from? Well, it all starts with the sun. The sun's energy, or solar insolation as scientists call it, is the fuel. But here's the absolute key. That fuel isn't spread evenly across the globe, not even close.
Think about it like this. Because the Earth is round, sunlight hits the equator like a laser pointer aimed directly at a wall. All that energy is focused on a small spot, and bam, it gets super hot. But at the poles, that same amount of energy from the sun is smeared across a huge curved surface. It's way more spread out, which means it's much, much colder. And this simple temperature difference is what kicks our entire weather engine into gear.
So let's start our journey right where the action is hottest, the tropics. The circulation here is run by this gigantic looping system called the Hadley cell. This is the first and, honestly, the most powerful gear in our whole global machine. Our trip starts right here, at 0 degrees latitude, the equator. Just picture the sun beating down all day, every day. It's heating up the land, the oceans, and of course, the air right above them. All that incredibly hot air gets light, and it has only one direction to go, up. And here is where the magic really happens. As all that warm, humid air shoots upwards, it creates a zone of low pressure. Now, as it climbs higher, it starts to cool down, and all that water vapor it was carrying can't stay as a gas anymore. It condenses, turning into tiny water droplets, just like the steam on your bathroom mirror after a hot shower. That condensation builds clouds, and those clouds lead to rain, a lot of rain.
Now, this isn't happening in random spots. It creates this massive, permanent rain-making belt that circles the globe. It's called the Intertropical Convergence Zone, or ITCZ for short. And this explains perfectly why the world's biggest, luscious tropical rainforests are parked right along the equator. They're a direct product of this constant, rising, rainy air. But remember, what goes up must come down. That air can't just keep rising forever. Way up in the atmosphere, it spreads out, heading north and south. By the time it gets to about 30 degrees latitude, it's cooled off, it's dropped all its moisture, and now it's heavy, and it's got nowhere to go but straight back down.
And get this, there's a fascinating piece of history tied to this exact spot. These latitudes are known as the horse latitudes. Back in the age of sail, ships would get totally stuck here for weeks because the sinking air means there's almost no wind. And the legend goes that to save their precious drinking water, the crews were forced to throw their horses overboard. It's a grim story, but man, it paints a vivid picture of the weather right here.
So as that cold, dry air sinks, it creates the total opposite of what we saw at the equator. It creates a zone of high pressure. And high pressure means clear, cloudless skies and pretty much no rain at all. Now, take a look at a map. Where does this happen? It's exactly where we find the Sahara, the Arabian Desert, the deserts in Australia. So there you have it, the first half of our answer. The very same system that creates rainforests at the equator creates deserts at 30 degrees. Now, once that sinking air hits the ground, it splits. Some of it flows back toward that low-pressure zone at the equator, trying to fill the gap. But because our planet is spinning, the wind doesn't blow in a straight line. It gets a twist, creating steady winds that blow from east to west. And these are the famous trade winds. They got their name because they were so reliable, they powered the sailing ships on all the old trade routes. And that right there completes our first big loop, the Hadley cell. But what about the rest of that sinking air? The part that didn't flow back to the equator? Well, it heads toward the poles, and it's the main driver of weather in the mid-latitudes. Places like Europe and most of the US. This brings us to the second gear in our machine, the Ferrel cell. And here, the whole wind pattern flips. The air moving from 30 degrees toward the poles also gets deflected by the Earth's spin, but it twists in the opposite direction. These winds blow from west to east, which is why we call them the westerlies. It's the reason why weather systems in the United States generally travel from the west coast toward the east coast. So let's follow that warmer surface air on its journey. Around 60 degrees latitude, we're talking near places like the UK or southern Alaska. It's about to run into something big. It's on a collision course with freezing, dense air that's sliding down from the poles.
So what happens when these two completely different air masses smash into each other? Well, the warmer, lighter air from the south can't push through the heavy, cold polar air. It has no choice but to rise up and over it. And what have we learned about rising air? It creates another zone of low pressure, which means, you guessed it, clouds and precipitation. This is exactly why places like the United Kingdom have a reputation for being so cloudy and rainy.
All right, time for the final piece of our three-part puzzle, the polar cell. This little engine operates over the highest latitudes, putting a cold cap on the top and bottom of our planet and completing the entire global picture.
Let's go all the way to the end of the line, 90 degrees north and south, the poles. Up here, the air is unbelievably cold and dense. It just cools and sinks, creating this permanent cap of heavy air at the top and bottom of the world.
And here is a fantastic fact that might just blow your mind. Just like we saw at 30 degrees, this sinking air creates a powerful zone of high pressure. That means clear skies and almost no precipitation. It is so incredibly dry, in fact, that both the Arctic and the Antarctic are technically classified as deserts. That's right, polar deserts.
And to finish it off, that cold, dry air on the surface flows away from the poles, heading back towards that 60-degree mark. And just like the trade winds near the equator, the Earth's spin gives it a twist, creating the polar easterlies, which flow from east to west. And that completes the third and final loop in our system, the polar cell.
So we've looked at three different cells, the Hadley, the Ferrel, and the Polar. But the biggest takeaway here is that they aren't separate things. They're all interconnected gears in one single, incredible, and beautifully complex machine that wraps around the entire planet.
So let's just do a super quick recap of the whole system. The Hadley cell gives us those lush rainforests at the equator and the big deserts at 30 degrees. The Ferrel cell is the reason for all that unpredictable, often rainy weather around 60 degrees latitude, and the Polar cell explains why the coldest places on Earth are also some of the driest. From the steamy tropics to the frozen poles, this three-cell system defines our world's climate.
This entire global engine is powered by a simple temperature difference between a hot equator and cold poles. It's a machine in a really delicate balance. And that leaves us with a huge critical question for our time. If we start messing with the fuel by warming the whole planet and changing that fundamental temperature difference, what in the world happens to the engine itself?